Hello friends, warm welcome. This is a continuation of the video lectures on Fourier transforms, and this video is focused on the topic convolution. So in this video we shall first begin with defining what convolution means, and then we shall proceed to state and prove the convolution theorem, which is used using Fourier transforms. Convolution basically it is a mathematical operation. When I say it is a mathematical operation which we denote by the notation star on two functions, say f of x and g of x, that produces a third function, say f star g of x. And what does this f star g does is it expresses how the shape of one function is modified by the other. So this is what f star g does. It expresses how the shape of one function is modified by the other function. So the mathematical operation called star is the notation for convolution of two functions, and which will finally give us a new function, and that will talk about how is the shape of the first function modified by the other function. It's a very important technique, especially in digital signal processing. I'm sure we are all well versed about this particular paper called Digital Signal Processing, and in which we talk about the mathematical way of combining two signals to form the third signal, and that's where convolution plays a very vital role. It in fact convolution relates three types of signals. One is the input signal, one is the output signal, and the other is the impulse response. And this convolution relates these three types of signals in digital signal processing. So a very important topic to be known to understand this particular subject. Apart from digital signal processing, convolution finds applications in image processing, in audio processing, in artificial intelligence, in optics, probability theory, even in multiplication of polynomials, and many more. So, a very widely ranged topic is what we are dealing with at the present moment, called convolution. So let us begin first of all by defining what is the convolution of two functions initially, and then start off with the statement of the convolution theorem. So if f of x and g of x are taken to be two functions, then convolution of two functions is denoted by f star g of x. Now this can be defined as per the transform that we are dealing with. Here we are talking about Fourier transforms. So I shall define the convolution as 1 by root 2 pi integral limits varying from minus infinity to plus infinity. One function is a function of t, where t is the variable of integration, and the other function g is a function of x minus t, and the integration is performed with respect to t. Now this is the definition of convolution. So the convolution of two functions, which is denoted by f star g of x, is denoted by 1 by root 2 pi integral minus to plus infinity f of t g of x minus t dt. But a peculiar property of this, which is where which function should be written as a function of t, which has to be written as a function of x minus t, need not be confusing, because the convolution operation satisfies the commutative law, that is f star g is equal to g star f. So it is immaterial of which function is written as a function of t, and which other is written as a function of x minus t. So you could write it either way, the result is obtained. So this is the definition of convolution, and making use of this definition, let us proceed further to state the theorem called convolution theorem. So this is a very important theorem, very widely applied. We have also have a similar theorem for Laplace transform, and I'm sure people have learnt that theorem too. So now let us state this particular theorem. The statement of the theorem goes this way. the Fourier transform of the convolution of two functions. So if f and g are two functions, then the Fourier transform of the convolution is equal to the product of the respective Fourier transforms. That means the Fourier transform, if f of x star g of x is what you have, because f star g of x can also be written as f of x star g of x. So Fourier transform of that convolution is equal to the product of the respective Fourier transform. So if we take the product, the Fourier transform of f of x as f of s and the Fourier transform of g of x as g of s, then the Fourier transform of f of x star g of x is nothing but f of s multiplied by g of s. Now this is the result which gives us in this convolution theorem. Let us now start off by proving it. So we shall start the proof by starting with the left hand side and arriving at the right hand side. We shall begin with the basic definition. By now all of you must be familiar that Fourier transform of f of x star g of x. It's only by replacing f of x in our definition by f of x star g of x. It is given to be 1 by root 2 pi integral minus to plus infinity. Instead of f of x, we are writing f of x star g of x. Of course, the kernel, I am sure you all agree, it is e power isx multiplied, and then you are integrating with respect to x. Now what we shall do is, in place of f of x star g of x, we shall substitute what is the definition of convolution. So star says convolution and our definition says this. Now if I call the definition to be 1, I am going to substitute that 1 in this place, f of x star g of x. What should I write it as? 1 by root 2 pi integral f of t g of x minus t dt. So let's proceed and rewrite it here and see what happens. This becomes 1 by, I will continue with the same color. So it's 1 by root 2 pi integral minus infinity to infinity is as it is. Now what are we writing? We are writing that definition in this place. So let me put a bracket there and rewrite the definition of the convolution as 1 by root 2 pi integral minus to plus infinity. Note that the outer integral which we are writing is for the variable x. Now what are we writing? It is for t. That is how our definition went. F of t, g of x minus t. Then you complete by writing dt. Close the bracket. So now you have finished with f of x star g of x, and the remaining part of the integral is e power isx dx. So this outer integral is for x, inner integral is for t. Now let us now combine and rewrite it as an ordinary double integral by pulling the constants. So it's 1 by root 2 pi into 1 by root 2 pi. I have double integral. One is for x and one is for t. So x varies from minus infinity to infinity. T varies from minus infinity to infinity. F of t, g of x minus t, e power isx dt and then dx. So now I have just combined everything and expressed it as a standard double integral. Now according to my present stage, the inner integral is for t and the outer integral is for x. But if you notice that all the four limits are constants, and so what we shall, even if we try to change the order of integration, that is writing the interval, what do you mean by changing the order? Outside you write it for t and inside it is for x. Then also the limits will remain the same because all the four limits are constant limits. So the constant limits will not change when you change the order of integration. So we shall perform the changing the order of integration. So let me write here, changing the order of integration. I am going to just rearrange because there is no problem of limits here. I shall rewrite the double integral in the following manner. So this becomes 1 by root 2 pi. Alright. Now I will also keep this 1 by root 2 pi as it is for now, and then we shall take it inside. I told you outer integral should be for t, isn't it? So outer integral should be for t. So t will be from minus infinity to plus infinity. And which is the term having t alone there? If you notice, t alone is f of t. So I can attach that f of t along with this interval because this integral has t in it. So let me put f of t there. Then I open a bracket and now write the integral for x. X now varies from minus infinity to infinity. Collect all the terms which have x in it, this term has x in it, this term has x in it. So I will have to put them together. G of x minus t e to the power isx. And then you have, because you are integrating the inner integral with respect to x, you write dx. Close the bracket now and then write dt. We have now completed the changing the order of integration. What did we do? We simply interchanged the two integrals of x and t, writing t outside, and we combined the term. Along with that integral, we took up the term containing t alone, which is f of t. The remaining two terms had x in it, and so we attached it with the integral which is pertaining to x. Integration is done with respect to x. Outer integral is done with respect to t, and this completes the rearrangement of the integral. Now we shall perform a substitution to make it more simpler. So I shall take this argument. What is the argument given? X minus t. So I shall take u to be equal to x minus t. So what does that mean from here? This means x is equal to what? So x is equal to, from here, u plus t. So what is dx equal to? And that will imply dx is equal to du. That means I am changing the variable x to u. So I'm changing the variable x to u, keeping t as it is. So what will happen to the limits when x tends to minus infinity? When x tends to minus infinity, u also tends to minus infinity. Similarly, when x tends to infinity, u tends to infinity. So the limits are not changed. Let's proceed further. So now let us apply that substitution in this inner integral, keeping the outer integral as it is. So t varying from minus infinity to plus infinity, f of t goes as it is. Now let us change the integral. Now the integral, what is happening? U limits change from minus infinity to infinity. There is no separate limit change, so it continues to be the same. Let us write x minus t as u. Then let me write is. What is x now? X is nothing but u plus t, as you can see from here. And then what is dx? Dx is nothing but du. So I have changed the variable x to u successfully. And then outside that I have continues to be dt. So now what have we done? We have just applied the substitution that we have made from variable x to variable u. Now, you see there is something which is interesting here. Within the inner integral, I have a t term that is occurring there. See, ist is there. And normally what are we doing? We are combining the t terms with the outer integral. So we shall now rewrite the t term alone outside. So it becomes 1 by root 2 pi integral minus infinity to infinity. Yes, 1 by root 2 pi, I can attach it here, and then I can take that minus another 1 by root 2 pi inside. So here it becomes f of t. I am taking that e power ist outside. Okay. And then what is remaining there? Again, let me put a bracket. I take that constant inside, 1 by root 2 pi integral u varying from minus infinity to infinity g of u. I have removed this term. So this is not there anymore. So what is left there? Isu alone, du, and outside you have dt. Now you see, this is a separate integral, that's a separate integral. You can now rewrite this as a product of two integrals, and you see what happens to this. It is 1 by root 2 pi integral t varying from minus to plus infinity f of t e power ist dt. This is one integral, this is one term which I put it in a bracket, and into the next one is 1 by root 2 pi integral u varying from minus infinity to infinity g of u e power isu du. If you note here, both remind you of the Fourier transform definition, but for different functions. Now this is nothing but the Fourier transform of f of t, and this is nothing but the Fourier transform of g of u. But because I told you that t, u, x are all dummy variables, this is nothing but the Fourier transform of f of x into the Fourier transform of g of x, the reason being changing the dummy variable. So changing whether it is t or u, we are going to write it in terms of x because all are the same. We have changed the dummy variable and finally proved the result that the Fourier transform of f of x star g of x is the same as equal to the Fourier transform of f of x, which is f of s, into the Fourier transform of g of x, which is nothing but g of s, and hence proving that the Fourier transform of the convolution is equal to the product of the respective Fourier transforms, and that proves the convolution theorem. So let's go back as a summary and see what all we have done in this video and then conclude it. So we started by understanding the definition of convolution of two functions. So defining it in the terms of f of x star g of x or f star g of x in this manner, we called it 1. And we said that the convolution operation satisfies commutative law. And then we stated the convolution theorem as the Fourier transform of the convolution is equal to the product of the respective Fourier transforms. So we started by writing the Fourier transform of the convolution, substituted the definition there, then performed the change of order of integration, which was easy because the operations, the limits were all constants. Then we took a substitution for u to be x minus t and then rewrote it as a product of Fourier transforms, changed the dummy variables t and u to x, thereby proving the result. So this is a very important and a very applicative particular theorem. We shall apply this in problems too and also use it to derive another important theorem called Parseval's theorem, which I shall do in my next video. Thank you for watching. Take care.